Welcome back to our lecture series on Material Science and Metallurgy subject. This is Dr. L.Bhanu Prakash, working as Associate Professor in the Department of Mechanical Engineering at MLR Institute of Technology. So today's topic is on ferrous alloys, and within ferrous alloys we are continuing from our discussion with cast irons. So cast iron, so far we have covered grey cast iron, ductile cast iron, white cast iron, and today's lecture we will see malleable cast iron. And towards the end, we will try to compare all the cast irons, and we will discuss selection guidelines as well. In today's presentation, so we will be talking about mainly malleable cast iron, its composition, microstructure, properties, limitations, and applications we will cover. In addition to that, a short comparison of all cast irons with respect to their mechanical, thermal, and other physical properties, and what is the selection criteria that we have to take it for a particular cast iron, for picking up a particular cast iron. We will discuss about it, and we will summarize our lecture and discuss the key takeaways. So malleable cast iron, it is a heat treated cast iron which is basically derived from white cast iron. So as we have discussed in the previous class, so plain white cast iron can be the source for producing the malleable cast iron. So our starting material is white cast iron, and we will be heat treat it so that we get the malleable cast iron. So during this process, the cementite deposits into temper carbon nodules in a ferritic matrix. So cementite Fe3C, it will be decomposing, and the carbon in the nodules that will form in the ferritic matrix. The key features are, it is combining the castability of white cast iron, and the ductility of steel can be observed here. So on a historic note, this is the first patented in 1820s, in the 19th century, early 19th century, which has in turn it has revolutionized the early applications in automotive as well as pipe industries. It has been extensively used during those days because of its properties, its castability, the fluidity that you get it in the white cast iron, as well as the ductility of steel can be observed with this material. If you look at the composition, malleable cast iron is a white cast iron which is modified by heat treatment process, as we have discussed. So it is being produced from white cast iron by heating it and holding it 816 to 954 degrees centigrade. So we'll be heating, the heat treatment temperature is 816 to 954 degrees centigrade. So above the eutectoid temperatures. Then slowly cooling them at a temperature range of 704 to 760 degrees centigrade. So you have two sets of heat treatment cycle. So one set is heating up to and holding it at 816 to 954 degrees centigrade, and then cooling them to a temperature range of 740 to 760 degrees centigrade. That is another set of heat treatment process. It will be done in two stages. What it causes? It causes decomposition of cementite Fe3C and formation of graphite, that is a carbon, which exists in the form of clusters or rosettes. So graphite will be present again, that will be in the form of clusters or rosettes, which has been surrounded by the ferritic or perlytic matrix. Ferritic or perlytic matrix, depending on your cooling rate. If you do the slow cooling, this will be the slow cooling. Slow cooling, you end up with the ferritic matrix, and fast cooling can be with a paralytic matrix. So in malleable cast iron, again graphite is coming, and you will be noticing the decomposition of cementite, Fe3C iron carbide. And again, graphite will be back, and graphite will be present in the form of clusters or rosettes. So we have observed this same in the gray cast iron as flakes, and in the ductile cast iron we have seen them as spheroidal nodules. And white cast iron, there is no graphite, there is no presence in the white cast iron. There is no presence of graphite in the white cast iron, and again in the malleable cast iron we are bringing back the graphite in the form of rosettes or clusters. If you look at the composition, so the breakdown of iron carbide, so Fe3C will break down into iron and carbon, which is basically graphite, in the form of graphite. So it produces the graphite in the form of aggregates. Aggregates are clusters, which is known as temper carbon. These aggregates or rosettes or clusters are known as temper carbon. So these are not flake form. These are not in the flake form, and are thus causes the less damage to the mechanical properties. What is the problem with the flake form? If it is in the flake form like this, it will be having the sharp tips. So because of this sharp tips, it acts like a stress concentration region, and which will deteriorate the overall mechanical properties. So that is not occurring in the malleable cast iron, since there is no presence of flakes. Flakes are not present. It is present in the form of aggregates or clusters. So the result is material which possesses a good measure of strength combined with the ductility. So as there is no form, there is no presence of flakes, and it is present as the aggregates, so it offers the strength which is combined with the ductility. Composition, particularly carbon is less than 3%, you can notice. So it is 2.2 to 2.9 percentage, unlike in all other cast irons where carbon percentage is relatively higher. And again, silicon is coming at good proportions, 0.9 to 1.9 percentage, which is again close to above 1 percentage, which is, as we have discussed, which promotes the graphitization. It promotes graphitization, so it controls to avoid the graphite formation during casting. So silicon promotes the graphitization process. Decomposition of Fe3C. We will also have a small portion of sulfur here, which is less than 0.2 percentage, and phosphorus also less than 0.1 percentage, which basically minimizes the brittleness. So anyway, Fe3C is decomposing, so we'll be having a very minimum amount of cementite that will be present in the material, and that cementite, which is basically the root cause for hardness of the material and the brittleness of the material. So that has been substantially brought it down, and what is been in our hands, so we get the ductility. So we get the ductility as the brittleness is decreasing, so we get the ductility here. So this is the microstructure of malleable cast iron. You can see these are the aggregates. So the black region, these are the aggregates of graphite. So these are the aggregates of graphite. Aggregates are clusters. It's also called rosettes. So the remaining this region, this is like ferritic or matrix. This can be ferritic or paralytic matrix. So depending on the cooling rate, we get ferritic matrix or paralytic matrix. So in the malleable cast iron, we can again see the graphite, which is in the aggregate form. Dark graphite rosettes you can see, which is called as temper carbon which is here. This is called as a temper carbon. So temper carbon nodules avoids the stress concentration, that is no sharp flakes. So these aggregates, you can notice there is no sharp ends here. There is no sharp needle-like structures where stress upon the external loading, so stress can concentrate over that region. So that is not there with this. That is not there with this material, malleable cast iron. So some of the properties are discussed. We have two varieties. One is a ferritic malleable cast iron. Then we have the paralytic cast iron. Paralytic malleable iron is there. So hardness is relatively lower when compared to the white cast iron. So it's very high. So this is even though the raw material is white cast iron. So all the cementite that is present in the white cast iron, that is getting decomposed and forms into the graphite, which is in the aggregated form. And so its hardness is dramatically reduced when compared to white cast iron, where you can notice the ferritic malleable iron is ranging between 110 to 170 Brinell's hardness number, as well as in the paralytic it is close to 180 to 280 BHN. A tensile strength, as it is offering good strength, relatively better strength is, you can see here, 350 to 450 MPa, and in paralytic malleable iron you can see again 500 to 700. And why ferritic is lower and paralytic is higher? So in the perlite again it is alternate layers of alpha ferrite and cementite. So cementite again little bit carbon percentage is higher. As carbon percentage is higher, you get your strength. So that's why here tensile strength is little higher, and the ferritic is purely ferrite, alpha ferrite, so which is relatively soft in nature, and so the strength is always paralytic matrix will offer better strength when compared to the ferritic matrix. Elongation is also good. Elongation, since this is very soft, ferritic is very soft in nature, you can see elongation is 10 to 18 percentage, whereas here in the paralytic malleable iron the percentage of cementite is little larger, and so the elongation is relatively very small, almost 5 times lesser than uh, 3 to 5 times lesser than the elongation of ferritic malleable iron. So we have to make a choice. Choose the ferritic for bending applications and paralytic for load bearing parts. So where you want strength is your prime motive. So you can opt for paralytic matrix, whereas bending or little flexibility is needed in the application. So we can opt for ferritic malleable iron. So it offers good missionability, softer than the white cast iron. So white cast iron, because of the presence of Fe3C hard material, so it is missionability is like unmissionable. We have seen it's only grindable, but it is missionability is almost like negligible. Missionability is highly challenging with the white cast iron. But this one, since we are decomposing the hard carbides here, so we get good missionability back. Then similarly, we get the good impact resistance due to the ductility, but and this impact resistance is superior to the gray iron. It offers uniform properties, and there is no section sensitivity here. So it offers throughout the material, it offers uniform properties. Malleable cast irons are a class of cast irons with mechanical strength properties that are intermediate to those of gray and ductile. So you can write it. Malleable is situating. Ductile is the highest. You get the best in the ductile, and it is higher than the gray and lower than the ductile. So it is between uh, gray and ductile. Malleable cast irons are ideal for applications where toughness and missionability are required. So if we require toughness in addition to the missionability properties, then we can go for malleable cast iron. And for the components that are required to have some ductility or malleable, so that they can bend or fixed into position without any cracking. So in such applications, malleable cast iron is required. So if you are seeking for good strength, good toughness, good machinability, and little flexibility, if you are seeking for, then your option could be malleable cast iron. It has certain limitations as well. It's as I mentioned, it is heat treatment process is longer. It's up to 50 hours, almost 2 days, more than 2 days it takes. So almost 50 hours it will take, and it is as it is 2 days of longer duration, so it is very intensive. Sorry. So it is very energy intensive. So a lot of energy is being consumed here. Why it is long heat treatment process? You have two heat cycles, that is two stages it is happening. So one is to heat it and hold it at 800 and above temperature, and one you have to two stages basically. One you have to do while cooling, you have to maintain it at 700 to 740 degrees centigrade. So because of these reasons, uh, it will be having longer heat treatment cycles, which is very energy intensive. It has thickness limitations as well. So it is only suitable for thin sections which is less than 50 mm. So thicknesses for these components which are having less than 50 mm thickness is only applicable here. So larger thicknesses is highly challenging to produce. These are the two limitations that we have it with malleable cast iron. So if you look at applications, automotive sectors, you find it steering knuckles. Steering knuckles are manufactured with the malleable cast iron, where you require little ductility. And differential cases also, where you are seeking for ductile material property. So it should give certain warnings. In both the cases, it should give certain warnings before its final failure. So we don't want materials which will be failing catastrophically. Pipe fittings also, elbows and tees, threadable ones is also possible due to ductility. Hardware segment, if you see the wrenches, brackets, and chain links, no, these are basically made out of malleable cast iron. So it offers good strength as well as slightly the flexible in nature, right, and machinable. And these are basically thick. These are not the thick components. These are thin sections basically. These are thin sections that we are making out. So in the hardware segment, whatever wrenches that we see, that we come across in our day-to-day life, and brackets, chain linkages, all these are made out of malleable cast iron. In railway segments, coupler housings are also made out of malleable cast iron. So vintage car axles were often malleable iron. Our good old cars, their axles are made out of malleable cast iron, where they are tough enough for rough roads. They have their strength limitations, but though they are tough enough to handle the rough roads. Since this material has been brought into in the 19th early years of 19th century, this has been observed. This has been produced for the first time. So since then, it has been used in automotive sector and different other engineering applications. So our old vintage cars, some of the components, axles and others, some of the components, you can observe that those components are made out of malleable cast iron. It has challenges as we have discussed. It is very energy intensive annealing heat treatment process is employed here, and it is limited to the thin sections. I think it is repeating here. So overall, we look at the comparison. So it is grey cast iron, we have it, ductile we have discussed, and white cast iron we have discussed, and malleable cast iron we have discussed. So first we will look at mechanical properties. So up to here, mechanical properties. So in terms of tensile strength, it has a ductile cast iron is offering excellent range tensile strength. So almost 400 MPa to 1600 MPa is also possible. Ultra high strength is also possible if it is tempered ductile iron, ADI. And after that, you have this malleable cast iron is also having good strength. It offers good strength. Then elongation percentage. Here you have it ductile. Again, it is offering very good elongation. Then hardness, as we are aware that white cast iron is highly harder material, very hard material. And then we have trade-off between ductile material also. You can produce yet harder yet stronger materials. And impact resistance is very low for gray because of stress concentration regions because due to the graphite flakes. And white cast iron, it is not suitable for impact resistance, almost nothing we would say, because it is very brittle in nature. So easily cracks can form in the material. So again, ductile material offers very good impact resistance. And after that, we have malleable iron is also coming next. So if you see the mechanical properties, ductile iron outperforms in strength and ductility balance. So you get good ductility as well as good strength. If you look at other properties, physical and thermal properties, the damping characteristics, gray iron offers excellent damping characteristics. Vibration isolation can be achieved with gray iron, which is primarily used for machine housing and bottom of the machines been manufactured out of gray cast iron. Then you have after that you have ductile iron is also offering better. Thermal conductivity is very good with gray iron. Graphite in the flake form is offering very good thermal conductivity. Then we have castability. So castability again due to its high fluidity and low melting temperatures, gray iron here it is offering greater castability when compared to other. So except malleable iron, it's a little bit fair enough. So we have gray iron is catching up in it's standing out when compared to all other cast irons. So in terms of mechanical properties, ductile iron is outperforming, whereas gray iron is because of its damping characteristics that makes it ideal for engine blocks. So how do we select when we have to select gray iron from the properties? Looking at the properties also, will be by now we'll be getting some clarity. Again, we will look at clearly. We will look at what are the scenarios where you can pick the right material, which cast iron to be picked. We have to choose gray iron when our primary agenda is to get very good vibration damping. So very good vibration damping is required, and also cost is critical as uh, gray cast iron is very less expensive among all the metals. So if you are looking at less expensive metal and also which offers very good vibration damping characteristics, then your first go is like gray cast iron. Then if you are seeking for good strength and ductility balance is required and that is your prime attention, then we have to choose ductile iron. So where it is offering strength up to almost 1400 MPa and ductility is also very good. And white cast iron is only when the wear and abrasion resistance is paramount. Something like mining industry and crushing industry, where wear and abrasion resistance is paramount. In such scenarios, one can choose white cast iron. If you are looking for good ductility and strength balance and thin sections, if you wanted to produce thin sections with good ductility is needed, then our go is malleable cast iron. So these are some of the critical scenarios where you can choose the right cast iron. So if you summarize, heat treatment will be transforming the white cast iron into a ductile structure which is malleable cast iron. So malleable cast iron, the initial material, the starting material is a white cast iron which is having excessively high amounts of iron carbide. Upon the addition of silicon, most of the iron carbide will decompose and forms into the graphite, and graphite in this scenario present in the form of aggregates or clusters. So which is basically offering the ductile properties to the material. So if you are looking for more ductile iron, more ductile variant of malleable cast iron, then look for slow cooling where ferritic matrix can be observed. And if you are looking for thin sections which is with good strength and ductility, then seek for relatively faster cooling, and you with paralytic matrix will offer that variant in the malleable cast iron. So this has been used, as we have discussed, malleable iron is being used in where ductility is required for your material, and also you need good castability. So when these two are the paramount, and also if you want to produce thin sections, thin components, which is less than 50 mm components, if you wanted to produce, then we can go for white, so malleable cast iron. So malleable iron is the 19th century marvel, still holding the nuts and bolts together. So it has been first observed in the material science in the era of 19th century, early 19th century, and but still we are holding it. Still in our engineering applications, we are working with this malleable iron material because of its properties. These are the references that I have followed for this slide content. So for the audiences to ponder on the question, here is a question for you to ponder on it. So why can't we make thick malleable iron castings? As we have been discussing, it is only suitable for thin sections, and why can't we use thick malleable irons? So the hint has been given here: slow carbon diffusion in thick sections. So carbon diffusion during the heat treatment process that is occurring. So this plays a critical role. So based on the hint, if someone can catch the answer, so please write your comments in the chat box. Okay, with this we will conclude cast irons, ferrous alloys, and in our next lecture we'll be discussing copper and copper based alloys, where we will see brass, bronze, and cupronickel materials. Similar to cast irons, we will discuss their composition, different classification, and its properties, and certain challenges or the limitations that we have, and also applications we will see in detail for all these three varieties of material. So thank you for joining for today's lecture.